Okay, I think we are live. Good morning, good afternoon, and good evening, everyone, and welcome to the first session of the Scientist.com AI Innovation Series. My name is Chris Peterson. I'm one of the co-founders and CTO here at Scientist.com, and today I'll be talking about how neural networks learn from the ground up and cover the architecture of these data structures, their feed-forward computation, backpropagation, and how they learn from the data sets that they're giving. So when I had the idea to give this presentation, the idea was to talk about how generative pre-trained transformers, ChatGPT, works all the way from the math to the language that comes out. When I started to build that presentation, I realized that that's way too much, and I tried to break out the attention mechanism. And when I broke that out, I realized you couldn't really understand the attention mechanism unless you understood word vectors and embeddings. And when I started to look at that, I realized you couldn't really understand that unless you understand neural networks and the math that goes into those. And I was kind of reminded of this quote: "If you wish to make an apple pie from scratch, you must first invent the universe." That's kind of what it felt like. But that's where we are in this. We're right at the beginning. This is part one of how large language models work. We are going to cover neural networks in what is frankly kind of excruciating detail. We're going to go all the way down to the math, down to the matrix multiplication and the calculus that is required to train them. So that's my little disclaimer right up front. The agenda of what we're going to cover today: first, we're going to talk about the structure of the neural network, what it looks like, what it's composed of. We're going to show how you feed data through it, how you give it numbers and get new numbers out the other end. Then we're going to show how we train it so that those numbers are actually meaningful, and that's through an algorithm called backpropagation, sometimes referred to as gradient descent, and we'll find out why. And then we're going to go through a real-life example. Okay, so first, network structure. So this is a depiction of a pretty simple neural network. All right, what you see here, these circles, these are called nodes, and the things that connect them are edges. So this is sometimes referred to as a directed graph. All of the nodes in all of these nodes are fully connected here. It's divided into layers, and each layer is fully connected to the next layer via edges. The first layer is called the input layer. So in this example, we have 9 nodes in our input layer. And each node will receive a number, a floating point number as an input. So it is important to realize neural networks, there's nothing about them that understands language. There's nothing about them that understands images. They only take in numbers and they compute, they perform a bunch of computations, and then they spit new numbers out. If you want it to understand language, if you want it to understand images, you have to first convert those to a series of numbers. The next layer is called the hidden layer. And it's called the hidden layer because it doesn't actually connect to the outside world. It takes input that's computed after the input layer, and it passes data to its next layer. This network that we're looking at here has a single hidden layer, but they can be of arbitrary depth. So here I'm showing one that has 2 hidden layers. It could have 10 hidden layers or 1,000 hidden layers. They can be as deep as you like, and often, or when you hear people refer to deep learning, what they're referring to is neural networks that have multiple hidden layers. They're deep in that regard. I am showing a network that is very symmetrical. It's got 4 nodes in this hidden layer, 4 nodes in this hidden layer. It's got 9 in the input and 9 down here. That's not a requirement. You can have neural networks that are all different configurations. You can have hidden layers that are wider than your input layers. Your input layer and your output layer don't have to be the same size. The symmetry is just an artifact of the example that we're gonna go through later. So this network is symmetric. That's not a requirement. And then finally, we have the output layer, and this is very similar to the input layer. It receives a bunch of numbers, performs calculations, and then the output of this layer is the output of your neural network. And then these layers are, as we mentioned, fully connected by edges. And those edges all have weights. The weights are really what make the neural network work. So I've zoomed in on a single node here in the hidden layer. Yeah, I've zoomed in on a single node here in the hidden layer, and you can see that each edge that's coming into that node has its own individual weight. And this is the same for the other nodes in the hidden layer. They each have their own set of weights that we're going to tune during backpropagation. And that is most of the structure of the neural network, but we do need to talk about what's called the activation functions. So each of these nodes has an activation function, and it takes the input that we're going to explain during feed-forward computation, and you run the activation function on it, and then it passes the results of that on to the next layer. So you've probably heard people describe neural networks as being based on the brain. Well, if that analogy, to explain that analogy, each one of these nodes would be a neuron. Each one of these edges would be a synapse. And then the activation function kind of controls the firing of that synapse, right? It controls the value that the network passes on. So if you hear people refer to it as being based on a brain, that's kind of that's where the analogy comes from. To my knowledge, it is pretty uncommon, or basically never happens, to have an activation function on your input nodes. I don't see why you couldn't, but that's pretty atypical. Your activation nodes, or your activation functions, are usually reserved for your hidden layers and your output layers. I did want to briefly talk about some of the activation functions that are used. We don't need to go through these in detail, but there are a variety of functions that you can use, and as you're constructing your network, you can use these different activation functions to get different behaviors out. We've got the identity function here, which is just f of x equals x. You've got some sigmoidal looking curves, and you've got some simpler straight lines down here. There's two important things to note about the activation functions. They always go from the bottom left to the upper right. They're always increasing. And they have a well-defined derivative. So each of these, here's the derivative function for each of these. We're going to get into why that's important later, but it is important that they have a well-defined derivative. And because they're going from bottom left to upper right, that derivative's always going to be positive. Okay, so that's the structure of the network. So let's take a look at how you actually use it to compute values. That's called feed-forward computation. So just in words, the way this works is you're going to feed a floating point number, just a number, 0.5, 1.1, into each one of your input nodes. That node, each one of those nodes, is fully connected to the next layer. You're going to multiply that input by the weight of the edge that connects it to the next layer. At the next layer, you are going to sum all of the results of those multiplications, and that will become the input to the hidden node. That node will take that input, run it through the activation function. The result of that activation function, it will pass to the next layer, and you will repeat. That was a lot. Don't worry. We're gonna go through it in detail. So here is a visual representation of that. I've kind of thrown some basically random numbers here as inputs. So the way, and I've zoomed in on that same node. This is going to be our example node that we look at as we feed forward through this network. So the way that you compute the input to this hidden node is you take this number times this number, plus this number times this number, plus this number times this number, and so on and so forth. So it'll be 0.6 times 0.05 plus 1.1 times 0.04. I've written it all out down here. And that's going to give you a number, 0.479. And that is the input to this node. And you'll do the same thing for this node, and this node, and this node. And that will be the input to the activation function on that node. Now, if you remember your linear algebra, or if you remember your matrix math, this formula might look familiar. This formula is essentially the formula for dot product. So this is the same exact algorithm that we just ran, just in matrix notation. So every number here, these are the same inputs, the same numbers that we saw in the inputs. So 0.6, 1.1, 0.6, 1.1. And these are the weights of the various edges. So 0.05, 0.04, 0.05, 0.04. Just a different notation for the same exact algorithm that we just ran. And to compute the dot product, you do exactly what we just did. This number times this number, plus this number times this number, plus this number times that number. And at the end, you get a scalar, which is the same number that we came up with. So the dot product is a very compact, efficient notation for what's happening to each node in as we're feeding data through that layer. But we're not doing just one node. We need to do all the nodes. And that is actually matrix multiplication. So what we've done here is all of the weights that connect to the third node become the third column in this matrix. And I didn't fill these in. These are just variables. But this is all of the weights that connect all of the nodes in the first layer to the first node in the hidden layer. These are the weights that connect all of the nodes in the input layer to the second node in the hidden layer, and so on and so forth. And to perform matrix multiplication, it is essentially just iterated dot product. So you take the dot product of this with this, and that gives you the input to your first node. The dot product of this with the second column gives you the input to your second node, and you'll do that across. This, I mean, we've all seen NVIDIA's stock price go through the roof, right? Because they make GPUs, and we've probably all heard that GPUs are good for AI and deep learning and LLMs and all of that. This is why. GPUs are exceedingly good. They are purpose-built to do matrix math. And we can very efficiently and compactly use matrix math to feed data forward through a neural network. And this is the method that we do that by. This vector is our input. This matrix is all of our weights. The multiplication of that gives us this vector, which is 1 by 4, which is the input to our next layer. Just a couple other quick notes. For matrix multiplication to be well defined, the notation here is row by column. The columns of the first matrix have to match the rows of the second matrix. So the inner dimensions here have to match, otherwise the multiplication is not well defined. And you end up with a matrix that has the outer dimension. So we're going to see this over and over again as we change the dimensionality, as we feed forward and we backpropagate through. So I just wanted to mention that. Yeah, so that is matrix notation for feeding data through the layers. Now we have to run our activation function. That is the input to our hidden layer. I've chosen to use the sigmoid activation function. Right? And this is the graph of the sigmoid. And this is the function for sigmoid. It is 1 over 1 plus e to the negative x. The function itself doesn't really matter. But we saw here that our example node, the output was 0, or the input to our hidden layer was 0.479. So that becomes the input to our activation function. And when I run that, I get 0.617 and change as the output. And I drew a little red dot on our function there. Now we're going to talk more about derivatives in a couple minutes, but I did draw out the derivative of this function here. And you can see that, you know, our this point on our graph is at pretty well one of the steeper ones, which puts it at pretty high on the derivative graph here. So we're going to talk more about the derivatives in a second, but I wanted to call that out. Okay, now we have to reverse it for our next step. So now in the first step, we went from 9 input nodes down to 4 nodes in our hidden layer. Now we're going from 4 nodes in our hidden layer out to 9 nodes in our output layer. So the math is exactly the same, but the dimensions have changed, right? So this vector here, this is going to be the output of the activation function from our hidden node. And we see here our third node is 0.617, which is right here. These are the weights that connect it to the next layer. And I'm going to multiply my vector by this set of weights to get my input to my output layer, which is very difficult to say over and over again. And I've got some sample weights here. So to do that, I when I do that multiplication, I end up with an output or an input to my output layer of 0.417. And once again, we see that the inner dimensions here cancel out, and I'm left with a 1/9 matrix, which perfectly matches the size of our output layer. And once again, the 9 is arbitrary. It matches the input layer, but that is not required. If it was, if we had 5 nodes in our output layer, this would still be 1/4. This would be 4/5 for our 5 nodes in our output layer, and then you would be left with a 1/5 vector, which would still perfectly match our output layer. So this is very amenable to matrix multiplication. This is a visual representation of that. Here are the outputs of our hidden layer. Here are the weights, and you're going to multiply this number by that number plus this number times that number plus that number times that number. And that's going to become your input to this node in your output layer. And then the last step that we need to do to feed data through is we need to run our activation function in our output method. I've chosen sigmoid again. It's kind of atypical. We're going to use a different activation function when we get to the example, but this one's a little bit easier to show one off. So we take the output of this, which is 4.17. We put that into our activation function. We end up at a point that's actually remarkably similar to our last one. And this, once again, is the derivative. So this number here, 0.617, is the output of this neural network for that particular output node. And you're going to run that across all the nodes, and then those values will be the output of your feed-forward computation. So that's it. We've fed forward. But essentially, we haven't trained the network yet. So essentially, all we've done is create a very complicated and expensive random number generator. So how do we train this network so that those computations, that series of calculations, actually produces something useful? Well, that is backpropagation. So in a nutshell, what you're going to do is you're going to start with a data set. And this data set is going to have a set of inputs, and each one of those inputs is going to be correlated with a set of outputs, right? And those inputs and outputs are going to be vectors of numbers that match the size of your network. You're going to initialize your network with random weights. It might seem a little bit weird, but you're going to start with random numbers, and then we're going to train it to change those weights so that they're meaningful. Then you're going to feed your inputs through, right? And they're going to start off just like we did, basically generating random numbers. And you're going to do it. They typically do it in batches. We're going to do it one at a time so that we can see it. But you typically do it in batches. Then you compare what your network output to what the expected output was, and then you use backpropagation to adjust the weights. I realize that that's a little bit of a recursive definition, and backpropagation is doing a lot of work on that slide. So what is backpropagation? Well, the first thing we need to do is we need to assess the overall error in our network. This is something called the loss function. What is the loss of our network? So as we feed data through, how different are our expected outputs from our actual outputs? And that's going to be a single number. It's going to tell you like, oh, that you have an error of 5, or you have an error of 1,000,000. The number doesn't really matter. What you're looking to do is minimize it. From that number, you're going to compute an error signal. The error signal, the job of the error signal is to allocate different portions of that error to different portions of your network. Specifically, we're going to allocate different parts of that error, or different amounts of that error, to different nodes in your output layer. So you're going to end up with a vector that is the same size as your output layer. You're going to propagate that error backwards. That's what we're going to spend a lot of time looking at. But conceptually, it's very similar to the way that we fed inputs forward through the network. We're going to feed this error backwards through the network. And I did want to call out that the derivative of the loss function and the derivative of the activation function is going to be crucial in how we assess, or how we assign different portions of that error to different components of our network. And then you're going to repeat. This is an iterative process. Okay, so a little bit about the loss function, right? There's various loss functions you can use, right? You can imagine this as just kind of assessing, looking at the difference between the expected output and what actually was produced. There are a couple of characteristics that a good loss function has, right? That keep you from using just like a simple like subtraction, right? One is you oftentimes want it to be scale independent. Right? You might have nodes in your output layer where the expected output is 10, right? And your actual output is 11, so you have an error of 1. But you might have other nodes where the expected output is 0.1, and you get a 0.3 as your actual output. And your error, your absolute error there is 0.2, but relatively, that's a bigger error than your 1, right? Than the 1 from the other node. So you want it to be scale independent. You don't want error from large expected values to swamp out error from small expected values. It should properly account for negative numbers, right? So if you had 2 nodes in your output layer that were expecting 10, and one of them got a 15 and one of them got a 5, you don't want an error of 5 and an error of -5 to cancel out and give you an error of 0, because that's not that's not a useful way of looking at the error of your entire network. And finally, in some use cases, you want your loss function to properly account for probability distributions. Right? So a lot of times what we're doing with these neural networks isn't computing a value. We're computing a set of values, a probability that a result falls into one of these bins. And so you oftentimes want to compare how different is this entire distribution to this other distribution, and those are a different type of loss function. And finally, at the risk of sounding like a broken record, it must be differentiable. And now we come to the portion of the presentation where differentiation becomes required. So how do you get from your loss function to an error signal, right? Remember, your loss function is going to output a number, a single number that tells you how well your network captured or related the input to the expected output. And you need to turn that single number into a vector that is the same size as your output layer. To do that, we need to talk about derivatives. So let's back up a little bit. Let's just refresh on what a derivative is. So you'll recall that the derivative of a function is the slope of that function at any point, right? So I've got a function here, another sigmoidal type curve, and I've got the derivative of that function below it. You can just visually see that this function is steepest around 0. That steepness means that it's got a high derivative, and you can see that in the derivative function. Its highest point is at 0. And as you get further from 0, the line gets more shallow, the changes in y doesn't change as much, and out there your derivative is lower. So your derivative is telling you 2 things. First, it's the sign is telling you the direction of the change. So this derivative is really the derivative of y with respect to x. And if that derivative is positive, that means as x gets bigger, y is going to get bigger. If the derivative is negative, then as x gets bigger, y is going to get smaller. So the sign tells you which direction one variable is moving with respect to another. The magnitude of that derivative, the absolute value, just the size of the number, tells you how sensitive one value is to another. If the value is high, the slope is steep. If I, for an increment of x, I'm going to get a relatively large change in y. But if the derivative is low, if I'm out here around 2, if I take the same increment of x, I'm going to get a relatively smaller change in y. So the derivative, just to repeat, the derivative gives you 2 things. The sign of the derivative gives you the direction of the change, and the size of the derivative gives you the sensitivity of one variable to another. So what we've been looking at here is a pretty simple derivative. This is, a 2-dimensional function. You've got y, you've got x. It's a pretty simple derivative. Your loss function is much more complicated. Your loss function is multivariable. So specifically, your loss function is going to take as inputs each one of the outputs of your vector, or of your network. So in our case, we have 9 outputs. So your loss function is going to have 9 inputs, right? Instead of, y equals f of x or loss equals f of x, it's going to be loss equals f of a, b, c, d, e, f, g, h, I, right? Which is a lot of variables. That's 9 input variables. That's 1 output variable. That's a 10-dimensional space. That's a very hard thing to reason about or describe. So let's pull back and let's consider a much simpler network. Let's consider a network with 2 outputs. We can call that output 0 and output 1, or make it even simpler, let's call it output x and output y. So our loss function is now f of x and y, and that's a 3-dimensional function. That's a function we can kind of draw out. And if you were to draw that out, you would end up with a graph that looks something like this, right? We've got the x-axis along the bottom here. We've got the y-axis along the bottom here. For every value that your network could output, it's going to give you a loss value, and that loss is going to define a surface in this 3-dimensional space. So this surface is your loss function. And what your network is doing as you're training it is you're kind of exploring this surface, right? And remember, this surface represents loss, which you want to be minimized. So you're looking for low points on this surface. This surface is often called a gradient, which you are descending to find a low point, which is why this algorithm is often called gradient descent. You're descending the gradient to find low points in your error function. Okay, so where does the derivative come in? Well, we can't really, what we're looking at here with this scary looking d is what's called a partial derivative. This is the partial derivative of loss with respect to x. And what that means is if I don't change anything else, if I leave y entirely constant and I only change my x variable, when x increases, does loss increase? Does it get bigger? If it does, you've got a positive partial derivative. If it gets smaller, you've got a negative partial derivative. That means for every change in x, does loss get bigger or smaller? And does it get bigger fast? Does it get smaller slower? You're looking for, again, the derivative tells you the direction and the sensitivity. And you can do that for every variable, right? You're going to have a different derivative for y. If I held x constant, y might be increasing quickly. So it might have a very large positive derivative, but x might be getting lower slowly. So it might have a smaller negative derivative. And that, it's easier to visualize in 3 dimensions, but that is, you can extrapolate that to as many dimensions as you need. You can extrapolate that to 10 dimensions for our particular sample network. You can extrapolate that to 16,000 dimensions if you have a much bigger network that's computing something different. Okay, so to be perfectly honest, this is kind of the crescendo of the math. We're going to go through a lot more matrix stuff, but I'm just going to repeat that one more time. To get from your loss function, to get from that single number that represents the error associated with your entire network to a vector where you assign portions of that error to different nodes, you're going to take the partial derivative of loss with respect to that node, right? And that'll tell you if that output node, if getting bigger, will reduce loss, or if getting smaller will reduce loss. So what you're really looking for to reduce loss is negative derivatives associated with nodes in your output layer. Okay, I swear that was the crescendo of the math. So now we have our error vector. It'll match the dimensionality of our network. We're going to end up with 9, for our network, we're going to end up with 9 individual numbers. That is the error associated with each node in our output layer. We now need to feed that backwards through our network. We need to kind of undo what we did during the feed forward step. And the last thing that we did during feed forward was to apply our activation function. Now, the way you backpropagate you don't sort of like run it through the inverse of that function. Again, you take the derivative. All right, what you're looking for is how sensitive is each one of these nodes to changes in its input, because that's going to tell you where you can make changes to your network that will ultimately affect the error. And remember, our activation functions are always positive. So our loss function derivative could be positive or negative, and that's going to tell us the direction that we need to move these weights. These will always be positive. The sign isn't going to flip after you compute the derivative of loss, but it will tell you how sensitive each one of these nodes is to its input. So that's how you get from your error signal of your loss function to the error signal of your output layer. All right, so that is the first step of backpropagation. We've now undone the very last step that we did in our feedforward process. And now we're actually ready to adjust weights. So each one of these nodes in our error, in our output layer, is fully connected to each node in our hidden layer. The next thing we need to do is we need to apportion the error associated with this node with each one of the weights that contributed to it. And the way that we do that is we multiply the error associated with this node by the input that created that error. So to figure out how much we want to adjust this edge, we multiply this error by the input that it received. So this is the input that it got during the feedforward step. And then we subtract that value from the weight. Right? So that's what this is all saying. The matrix notation for that is a little bit different than the notation we had going forward. If you recall, going forward, we had vectors that represented inputs multiplied by matrices that represented weights. Here, we're kind of doing the opposite. We are taking, this is our error signal, right? So this is the vector that we're feeding backward into the network. This is the input that it received, and we're exploding that out into a full-blown matrix. And this matrix has the same dimensionality as our weight matrix, right? So once again, the math is exactly the same. So to get the value that I want to subtract from here, I multiply this by that. This is just a more compact notation for that. To get this number here, I multiply this number by this number. That gives me this number. This number by this number gives me that number. This is just a more compact notation for what visually we're doing here. This is also called the gradient. So this is the gradient of error with respect to all of your weights. This is essentially a matrix of how much you want to change your weights. You then subtract that from the actual weights, which looks like this. So you've got a bunch of weights here. These are the existing weights. These are this is your gradient, and then this is your new output weight. I think I got the math wrong here a little bit. But the thing I want to point out is you're subtracting here. And if we recall, the negative derivative at the loss function means that as that output gets bigger, loss gets smaller. So as that negative feeds backwards, you want to subtract it from the weights, right? So this negative gradient means that larger numbers will decrease the loss. So you take the weight and you subtract that negative number, which actually increases the weight, which will then increase the output of the network, which should reduce your loss function. And that is how you get new weights. That is the essence of the training process. There's also this learning rate here that I kind of skipped over. This is an external number that lets you sort of attenuate the gradient, lets you make it learn a little faster or a little bit slower, a little bit outside of the scope of what we're doing here. For this purpose, I have assumed it to be 1, but it is typically lower. So now we have successfully altered the weights of our first layer during backpropagation. And that is essentially, we're just going to repeat that over and over again until we get to our input layer. The last thing we need to do is to compute the error signal, which will assign error to each one of these nodes. Right? And the way we do that is we feed the error back through the network exactly the same way that we fed inputs in. So this error will be multiplied by this weight, this error multiplied by this weight, this error multiplied by this weight. You'll sum all of those. That's going to be the input to this. That'll be the raw error signal that comes into this hidden node. And once again, you're going to multiply by the derivative of the activation function to account for how sensitive this node is to changes in its input. And that's going to give you the error signal for this layer. And then you repeat, right? This is the same, this is a matrix representation of what we just did. So this is the same as when we fed forward. This is just feeding error backward through your network. And now you repeat the exact same thing that we did before, but we're at the input layer now. So you take the error signal times the input to come up with a new gradient, and that gradient is going to tell you how much you want to adjust every weight in this node, or in this layer, pardon me. And once again, the sign doesn't flip because the activation functions all have positive derivatives. So if it's negative, you still want larger weights, right? So you're still subtracting. And then you adjust your weights in this layer. And once again, this is the matrix representation of computing the gradient, and then the matrix representation of changing the weights. And that is backpropagation. I know there was a lot of math, a lot of matrices in there, but and the purpose of that is not so that you will remember, all of these exact functions or all of these exact formulas. The purpose of this is to help build a mental model of what's happening under the hood, so that you can see exactly how this network is learning, because I think that's really going to be critical when we start talking about embeddings and how these neural networks are used to compute the more, advanced techniques that we're going to cover in the rest of the series. So just to recap the backpropagation portion, the whole point of backpropagation is to minimize the loss function. The loss function tells you how well your network performed, right? You're trying to find a low point in that loss function so that your network is producing outputs that are close to the expected outputs. The way that you do that is you start with a data set. You're going to break it into a training set and a testing set. You'll probably hold back 20% of your data to test, and you're not going to train it on those. You're going to break that training set into batches. You might run, 10 inputs through at a time before you backprop and aggregate the results. Maybe you'll do 100. It's typically done in batches. We did it one at a time. You're going to run through your entire training set. Every run through that training set is called an epoch, and you're going to run multiple epochs. Right? You may decide ahead of time that you have budget to run 5 epochs, or you may decide ahead of time that you're going to run as many epochs as it takes to get to a certain value of your loss function, or you're going to look at the loss function, you're going to assess diminishing returns. At any rate, you're eventually going to stop training it, and the result of that training is going to be a network that minimizes the loss function. And what it is doing conceptually is it is looking for latent structure in your data set, right? Your data set hopefully came from real life. It came from some process that behaves, that conforms to rules, right? You might not know what those rules are. Those rules might be messy. They might be noisy, but there's some underlying structure to it. And what we've done by feeding the data forward and then backpropagating it and assigning errors to different components of the network is we're trying to extract that structure of your data set, and encode it into the weights of this matrix, or into the weights of this network. And that's kind of why the neural network works. It is expecting, when you feed in data it's never seen, it's expecting that data to conform however noisily it may be, it's expecting it to conform to the same set of rules, to the same structure that the rest of your data set is conforming to. And that structure has been encoded into the weights. And that's why neural networks can generalize to data that they've never seen before, because that data has to conform to the same underlying principles. If you were to just feed random data in, like if you were to just randomly generate a data set, it's not going to converge. It's not going to, it can't predict anything because there's no underlying structure. Okay, so that was backpropagation. Take a sip of coffee. Now let's get to an actual example. Tic-tac-toe. I've chosen tic-tac-toe because it is small and we can see what's happening. To be clear, you would never train a neural network to play tic-tac-toe. It's far too small a problem space. It wouldn't be worth it. But hopefully, it's small enough that we can see what's happening. So the first step in training a network to play tic-tac-toe is to encode the data, right? Network doesn't know anything about tic-tac-toe. It doesn't know anything about words or pictures or anything. You have to give it numbers. So what I'm going to do is I'm going to encode my moves as 1, my opponent's moves as -1s, and empty cells as 0. And I'm going to end up with 1, 0, 0, 0, -1, 0, blah, blah, blah. I'm going to stretch that out so that it is a row vector, 1 by 9. And we now see why our example network had 9 input nodes and 9 output nodes. It was all sort of back calculated from this example. So this is what a training example is going to look like. So in this example, my opponent, this time my opponent is X, puts a mark in the upper left-hand corner. And my expected output is going to be, I expect my network to respond by putting my mark in the center. All right, so that looks like -1 followed by 8 zeros, and then 4 zeros, 1, and 4 zeros. You'll notice I'm not outputting the entire board. I just want my network to output my move. And then this could have as many 1s and -1s in it as I want. And various training examples would. But for simplicity, we're going to have -1 and 1. So that's my training example. We've been looking at this neural network for 40 minutes now, probably. But just to rehash the hyperparameters, we have an input layer size of 9. We have an output layer size of 9. They both represent a tic-tac-toe board. The hidden layer is 4. Once again, it could be 10. Could be 50, could be 2. That is just something that you're going to set up ahead of time, and you would likely test different structures to see what worked for you. I'm going to continue with sigmoid as my activation function, but this time I'm going to use softmax as my output layer activation function, and as my loss function, I'm going to use cross entropy loss. So let's just spend a second and talk about these two. This is the formula. Don't have to remember it. The point of softmax is it is good for categorization problems. And that is essentially what we have here, right? I want my network to predict a category of what I should do, right? I want to know where on the board I should place an X. That's a category. That's a probability distribution. And that is the way the softmax behaves. It's very much like a probability distribution, but it is a probability distribution that nicely handles zeros and nicely handles negative numbers. So it's because the actual values are in the exponent, but it doesn't really matter. The output of the softmax is the entire layer will sum to 1, and because of that, you can treat each individual node as a probability that this is the node that is the answer to the categorization problem. So for our example, we want the center square to be our move. The output of the softmax is essentially going to be a percentage that says that's the % likelihood that this is your move. It always outputs positive numbers. This is a little bit of trivia that is kind of foreshadowing for future webinars. But this is asymptotic to 0. So as your inputs get smaller and smaller, or more and more negative, this number gets smaller and smaller. If you want your softmax to output a 0, you actually have to feed it negative 1,000,000, or I'm sorry, negative infinity. I misspoke. You have to feed it negative infinity to get the softmax to output 0. That's a little bit of trivia. We're not going to use it in this webinar, but we will use it in future webinars. And then finally, we have cross-entropy loss. Again, this is the method, or this is the formula for it. Formula doesn't really matter. The point is cross-entropy loss is one of those loss functions that is very good at assessing the differences between probability distributions. And again, this is essentially a classification problem. The output is going to be a single class, which is a single move, one of 9 possible moves. And the probability distribution will be the probability that each one of those cells or each one of those squares is where I'm going to put a mark. And cross-entropy loss compares the actual probability distribution of the network versus the probability distribution of the training set, which is always a bunch of zeros and a single one. Okay, so now let's feed this forward. We're not going to go through all of the math. We're going to do this a lot quicker than we did through the feed forward step. But this is how you're going to feed the data through. It's going to be, 1 followed by a bunch of zeros. This is randomly initialized, so I'm essentially going to get a bunch of random numbers out the other end, right? And random to a point. There is still structure to this because it's the softmax. All of these will sum to 1, and you can treat them as probability distributions. So what you're looking at right now is it's basically telling me that this node is the most likely answer, but it's random. It hasn't been trained yet. So it's telling me that I should move into the bottom left square. So how do we fix that? Well, first we need to compare it against our expected output. So here was our expected output, 0, 0, 0, 0, 1, 0, 0, 0, 0. I didn't bother computing all of the values, but you can just see visually that as this number increases, the error is going to increase because if this goes to 0.5, that will be further away from our expected probability distribution. So this is going to have a positive slope. As this number gets bigger, our ultimate loss is going to get bigger. Right? And that's true for this one, and it's true for this one. It's true for this one. It is not true for this one. As this one gets bigger, it gets closer to 1, our loss function, our loss in the network is going to get lower. So this is going to be the node that has a negative partial derivative, a negative error signal. And then the rest of these are all positive because as these get bigger, they get further away from the distribution we're looking for. So it's a bunch of positives, 1 negative, and a bunch of positives. So we now need to backpropagate that. You'll often hear this referred to as the chain rule. You're multiplying derivatives by derivatives of the same variable. And again, we're looking for how sensitive each one of these nodes is to its inputs. And again, these are all going to be positive. So the error signal after this is going to be positive, 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 negative, positive, 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 positive. You are now going to compute the gradient, right? And what I've done here is I've highlighted the edges, the weights that are going to get stronger because we want this node to output a higher number. So as it gets higher, loss gets lower. So the error gradient here is negative. And you're going to subtract that negative number from this weight, and that negative, a different negative number from this weight, and a different negative number from this weight. Subtracting negative is going to make those get bigger. So these weights are going to get stronger. These nodes are going to be more closely correlated with this node, right? And since these are all the opposite, all of these other weights are going to get a little bit lighter, a little bit, those weights are going to be a little bit diminished. Whoops, wrong way. We're then going to backpropagate the error to our hidden layer, same way that we fed data forward. We're going to multiply that by the activation function of this node. And again, we're looking for how sensitive each one of these nodes are to change. And then we're going to do it again. We're going to multiply that error by the input, and we're going to use that to adjust the weights. Now that error multiplied by 0 is going to give you 0, so we're probably not going to do much to these other weights. But here, that error times 1, that's going to give you a negative number, which you are going to subtract from the weights, thereby increasing these weights, correlating this node more strongly with this node, which is correlated more strongly with this node. And that is how backpropagation actually changes the weights so that it makes it more likely that the next time you feed this number or this vector through, that this number will be higher. That's pretty much the end. A few things that I did want to reiterate. Ultimately, I'm going to take this backwards, actually. I think the most important thing about a neural network is that it is extracting the structure of that underlying data set, right? There is implicit structure. There is a latent structure in that data set. There has to be, otherwise there's nothing to learn, right? Through this backpropagation method, you are encoding that structure into the weights of your neural network, and that's why when it's presented with new vectors, with new data that it hasn't seen before, as long as it behaves, or as long as it conforms to the same underlying structure, the same underlying rule set, those weights capture that rule set, and it should respond reasonably, right? The whole point of the neural network is to minimize the loss function. So the whole point is to make the actual outputs of the neural network match as closely as possible the expected outputs. You can very efficiently and compactly execute these neural networks using matrix math, and hopefully, again, the point isn't to remember all of it. The point is to expose you to it, build a mental model as to why that's true. And then we can use some calculus to determine how much of the error from our loss function applies to different components of our network, and we can adjust those components of the network to minimize that error. And that brings us to the end of the presentation. Let's see, there's a little bit more here. So once again, very happy to hear from anybody here. We're happy to take any questions you might have. As a reminder, you can submit questions using the Ask a Question tab on the right-hand side of your screen. So let me flip back to the window here. Okay. Looks like we do have a few questions here. I'm going to read the question, and then we're going to do my best to answer it. What are the differences between supervised and unsupervised learning in the context of neural networks? That's an excellent question. Got to pull that out of the recesses of my brain. Okay, so unsupervised, in a supervised model, I think it really has to do with where your data set comes from. In a supervised model, such as, well, let's pick on tic-tac-toe. You could do tic-tac-toe in a couple of different ways, right? If you were to manually set up a bunch of training examples for tic-tac-toe, that would be supervised, right? You have sort of told the network what it is you are expecting. But if you didn't do that, if you set up an algorithm to play tic-tac-toe and determine, which ones win and which ones are better, and you create the data set that way, that is more of an unsupervised algorithm. So we'll see this next time when we talk about word vectors. That is much more of an unsupervised thing, where it is taking data and it is kind of its own training set. So I guess that it's probably a somewhat unsatisfactory answer, but in an unsupervised method, it's kind of like the raw data is also the data that you're training to. So yeah, that wasn't maybe a great answer, but hopefully that helps. What are some of the common challenges in training neural networks, and how can they be overcome? I mean, I think the biggest problem you're going to face is coming up with a clean data set, right? I think that, getting a clean data set is probably the biggest challenge that I've had. This kind of relates to the supervised versus unsupervised. If you need to generate a data set that's more on the supervised side, that's more work, it's more data cleaning. An unsupervised, you're going to run into problems because the data is probably noisier, right? I think that an experienced data scientist is going to probably develop a feel for, whether or not you should have more nodes in your hidden layer or fewer nodes, or how many hidden layers you should have, or what activation functions you should use. I think coming up with that structure is a challenge, and varying your hyperparameters, the sort of meta parameters that define your network, is something that I think you probably get better at with time. But yeah, I think once you've got the structure and once you've got a clean data set, it's largely a matter of running the algorithms that we just talked about. Let's see here. Oh, someone suggested I turn the camera on. That's a great idea. Thank you. Okay. If the input vector is of a different dimensionality as the desired output, how does that work? For example, if I ask for a picture of a cat, it will generate a series of numbers that translates to the picture of a cat. Clearly, the output vector is much larger than the input text. So this is a challenge. Figuring out how you want to encode your data is a challenge, right? So let me pick on text for a moment, right? If you have a bunch of text, you're going to have, it can be of varying length, right? You need to, or let's pick on words. Words have, they vary in the amount of letters that you take to spell them. If you just took the letters as your input vector, you're gonna have a bad time, right? Like that's not going to be a great way to train your network. So that's where things like embeddings come in. Embeddings are a way of turning a word into a vector. This is going to be the entire next webinar, is how you do that. But it is a method of turning a word into a fixed size vector. That vector might be 64 elements long. It might be 256 elements long. It might be 16,000 elements long. But it turns a word into a fixed size vector. So the encoding step has to turn it into a fixed size vector. There are various ways that people deal with images. You will have things like recurrent neural networks, where you will take you will run through it sort of serially. There are convolution networks where you will take different sections of the image that are of the size that you need, and you can scale it up and down, and you can feed that through your network. So there are different strategies to do that. I think it's going to be very dependent on your specific use case. Okay, we got 2 more minutes. I'm going to try to answer one more question and see how we do. Here we are. This structure seems to depend entirely on the expected correct result for training. How does that work for large real-world data sets with crazy variability, or is it just a scaling problem? It is partially a scaling problem, right? We're going to see in 2 weeks, we're going to talk about embeddings. And embeddings are one of those sort of real-world, very noisy data sets. The goal of the network isn't, we're trying to minimize the loss, but I don't expect the network to output the exact right answer every time. It's going to output the thing that is closest to the right answer, but still might be kind of like a long way away. So you're, like if you're looking for a classification problem, I'm not expecting, in tic-tac-toe, I don't expect my network to output 0, 0, 0, 0, 1, 0, 0, 0, 0. It's probably going to output a bunch of lower probabilities and then hopefully a higher probability. It's not going to match sort of exactly. So my network it's approximating the answer. And as the data set gets noisier, you're going to have to expect somewhat more approximate answers. And you're going to have to probably train it on larger data sets for longer periods of time before you get to meaningful answers. But if there's an underlying structure, you should eventually converge on an answer that at least minimizes the loss function. Okay, I apologize to those of you whose answers I didn't get to. I will try to get to them after and contact you. Let's see, I think I have one more slide here. Oh yeah, so as a reminder, we have, don't know what that was. We have our next episode, or our next webinar in our AI innovation series in exactly 2 weeks. on Tuesday, July 9th. In that session, we're going to be talking about the role of word vectors and embeddings, which I kind of highlighted here in the question and answer section. And those are really crucial to the way large language models work. So I hope that if you found this interesting, please join us for that one, because we're going to build on the neural network stuff that we did today to explain how embeddings work. So thank you very much, and I hope to see you at the next webinar.